here we're going to work on the first question here. So it says answer the following based on butane, C4H10, which is used as a fuel in cigarette lighters. So it wants you to answer three questions. The first one, write the products of this reaction with oxygen. So it shows butane right here reacting with oxygen here. And that's going to produce something on this side right here. So the first one, they want you to write the products. The second one, they want you to balance the chemical equation and then rewrite it balanced, and then identify the reaction type. So on this one, we're going to actually start with C because it makes the most sense here and it's going to explain what comes over here. So you can kind of think about this one just logically. So since it's lighter fluid, what you're producing there is a flame. So it's going to be a combustion reaction. So the five answer choices that you have for reaction type are combustion, which is where you're combining a hydrocarbon, which is this because you have a hydrogen and a carbon, with oxygen, and you're producing some chemicals here, which are pretty much always going to be CO2, oops, and water, plus heat. Oops. Okay, so any combustion reaction is going to have this on the other side. And then we're going to balance it for part two. So this one right here, the answer to this is combustion. And you can think about that again, if you're using a fuel to create a fire, you're going to have to combust it like a fire. Okay. So this heat is important too because that's something that's part of what the characteristics are of a combustion. So H2O is going to be a liquid, and CO2, carbon dioxide, is going to be a gas. Okay. So the other types of reactions that this could be synthesis. So we'll go down. Let's find a blank space here. Okay, so synthesis is going to be when you're combining multiple things to become one. I'll just put synth here. So an example of that was carbon as a solid plus oxygen as a gas, and oxygen's one of those ones that's always two of them. Hydrogen same way. Okay, so oxygen gas leads to carbon dioxide gas. Okay, decomposition is the exact opposite. So decomposition is when you start with one molecule and you end up with more than one. So we'll call that decomp here. Okay, so that's going to be H2 CO3. Oops. 3 decomposes into water plus carbon dioxide. It's a gas. Okay. And then we have single and double replacement. So I'm just going to show one of those, and then you can kind of talk about what the double would be. But single replacement is where you have two molecules and you swap one of them. So for this one, we'll have zinc which is a solid. And you'll add that to, I believe this is copper sulfate, CuSO4. And that will turn into ZnSO4. Oops, cannot draw straight lines here. Plus copper. So the reason it's a single replacement, this zinc traded with the copper and became zinc. I think this is sulfate, and the copper stayed on its own. For the double, I guess we might as well just do that one too. Replacement. We're going to have hydrochloric acid plus sodium hydroxide, so NaOH. And then, so think about it this way. So on this one, we only had a single element here. This one we have a compound and a compound. So on this one, the H is going to combine with the OH. And this is, I know this is written differently than H2O, but we have 2 hydrogen and 1 oxygen, so this is the same as saying H2O. I just wanted to draw it out so you could see it clearly how this went here. And then on this one, the chlorine here will go here, and you'll have table salt, sodium chloride. So we replaced both of these. This one, we just did one replacement, boom, boom. This one went here, and then this one went here. So let's go back up to this. So this was combustion. So on a combustion, it's always going to be water, H2O, CO2, and heat. So that answers C, and it answers A. So we'll go to B here. So what we're going to do here is kind of make a table. So we're going to look at this as, different sides of this line right here. So how many of each element do we have on this side, and how many do we have on this side? So on this side right now, for C, we have 4 on the left, and we have 1 on the right. Okay. For H, we have 10 on the left, and we have 2 on the right. O, we have 2 on the left, and we have 3 on the right. We have the H2O, the one right here, and then this is O2, so we have 3 here. So this is where we need to kind of play some games to figure out how we're going to get from here to there and get it all to add up. So again, we got 2 H's, 3 O's, 1 C, and then over here we have 2 O's, 10 H's, 4 C's. So our problem here, and where it gets, where we have to actually look at this a little bit further, is that these two are tied together. So if I make this a 2 here, for example, then I'm doubling this and I'm doubling this. So let's look at our smallest ones first. We want to try to avoid doing changes to things that are going to make those way bigger first. So let's see right here. So let's start with the oxygens. So we know right now this has to be an even number of O's on the left side. No matter how many we multiply this side by, 2 times any number is going to be even. So first thing we need to do is come to this side and figure out how we're going to do that. So this one is O2, so we're in the same boat. This is where we're going to have to make our changes here. So the multiplier we put right here is going to have to be an even number because we need this number to be even so that we get evens all the way across. So let's just kind of pencil in a 2 here and see what happens. So if we have a 2 here, we have two O's, so that gives us 4, and we have two O's on this side. So we're thinking, okay, that's not terrible. We're not totally out of the running yet. But we have to figure out, okay, that means we do 2 here, and that gives us 4 H's here, 10 H's here. Okay, it's not going to work. So we have to figure out now is what conversion here is going to work. So we'll go over here. We'll try this one right here. So this one, like we said, it doesn't really matter how many O's we have here, because this is even and that's even. It doesn't really matter. We're going to figure it out. So let's put a little 4 here. So we put a 4 here. That gives us 4 C's and 4 C's. Sweet. That checks out. This gives us 8 O's here, 4 times 2. And we have 2 O's here. That's 6. So this would become a 3 to keep that working. 3 times 2. We got 6. Oh, excuse me. That's wrong. 8 and 2. That's 10. So we need 5 right here. Okay? Everything's still checking out except for our H's. So we're like, oh crap, what are we going to do here? So what we want to do here in our heads is we're thinking, okay, cool. We've got 10 right here. Just multiply this guy by 5. But we've already found out the 5 is not going to work here because this has to be even. So what we have to actually do here is multiply this one by 2. We have to be able to make this where we can get an even number here. Because if we do 2 here, let's draw that again. If we do 2 here, we have C, H, O. Okay, 2 times 4, we're going to have 8 on the left side. We're going to have 20 H's, because we have 2 times 10. We're going to ignore this one right now. So let's just got 2 O's. And on this side, again, we're going to ignore these little numbers we've been playing with, because we found out that our real constrictor is going to be this 2 right here. So we have 1 C, 3 O's, and we have 2 H's. Okay, now we're back in business. So this one, not going to change. We know that's the 2. Let's go over here and make those hydrogens make sense. So if we know this has to be an even number, and we know that this has to equal 20, because this is the only one we have on this side with H in it, 20 right here divided by the 2 here means we have to have 10 here. Okay, so what's that do to our numbers now? So now we have 10 O's here, and we have CO2 here. So we need to make our C's match now. Let's change this one so the C's match. So we have 2 times 4, so we have 8 C's. That means this number right here is going to have to be an 8 to make that 8 C's. So how many O's do we have now that we need to compensate for on this side? So we know this one's going to be 10. We know this one's 8. We know this one's 2. Okay, this side. 8 times O2 is 16. 10 times O is 10. So we have 26. So we need 26 oxygens here. But that doesn't mean we put 26 here because this is O2. So we have to do 26. That was terrible drawing. 26 divided by 2 equals 13. 13 over here. Okay, so now we double check our work. If these numbers have a common, like a factor between them, then that means we can simplify this down. But 2, 8, and 10 do. You can divide all those by 2, but 13 you can't. 13 is prime. Nothing divided or times itself is 13. So your final answer here is 2C4H10, and that's a liquid, plus 13, oops, make that more obvious, 13 O2, and that's a gas, oxygen gas, results in 8 CO2, and carbon dioxide is also a gas, plus 10 H2O, and water is a liquid, plus heat. There you go. Okay, that's how you do this whole one. So let's go down to this one right here. Okay, the first one. So you're taking a solid here, and you're adding it HOH, again we talked about, that's water, and then that's going to result in hydrogen gas and potassium hydroxide. Okay, it's potassium. Okay, so going back to that one we drew down here, so we have a single element, we're adding it to a molecule here, a compound molecule, and this K is pairing up with the OH right here, right there, and the H is getting left behind. So we have this reaction right here. We have a single replacement reaction. So that's part B on this one. Let's balance it out here first. So, okay, let's start here. So K, 1K on this side, 1K on this side, sweet. Now, hydrogen on this side, we have 1, 2 hydrogens, and you have 1, 2, 3 hydrogens on this side. Oh crap. So we're going to have to make this work here. We're going to have to make this an even number. So that way, because we have an even number on this side, so no matter what we multiply this by, if it's 1, 2, 3, 4, 5, whatever, it's still going to be an even number of hydrogens. So that means, let's just kind of pencil in a 2 here. Okay? And then we have 1 oxygen and 1 oxygen. But now if we have this 2, we have 2 oxygens here. So let's kind of keep moving along here and see what we have to do. So right here, we'll draw our little table again. We have potassium, oxygen, hydrogen. Draw our little line here. So let's start without this 2. Let's just start from scratch. Okay, we have 1 K on the left, we have 1 O on the left, and we have 2 H's on the left. On the right, we have 1 K, 1 O, we have 3 H's. So that's going to be our pain in the butt. So when we put a 2 here, let's draw it again. We're gonna use those same KOH lines here. If I put a 2 here, so left side doesn't change. We have 1, 1, 2. But now our right side, we have 2 K's. We have 2, 3, 4 H's. And we have 2 O's. Whoops. That should have been a 0. Should have been a 2 O's. Okay, cool. So how do we fix this? K's are easy. We put a 2 here. Okay, so that would give us the 2. That makes that match. The O's, this is where it gets a little more interesting. So we need to have 2 O's. So let's put a 2 right here. This gives us 2 O's, right? We have O times 2. That checks that off. And now we have 1, 2, 3, 4 H's. And then we have 1, 2, 3, 4 H's. Cool. I think that means we're good to go. We're going to double check it. So we'll drop one more time with these numbers that we penciled in here. On the left, we have 2 K's. We have 2 O's. And we have 4 H's. H and H times 2. On the right side, we have, let's start with K's. 2 K's. We have 2 O's. and then 2 H's here and 2 H's here. Oops, I don't know why it keeps coming out 0. Let me 2 and then 4. Cool. So that's it. So we literally, these are our answers. There's 2 here. There's 2 here. There's 2 here. And then this would just be a 1. So this one was single replacement. Oops. It's balanced. Cool. Single replacement. What would you observe at this reaction in front of the laboratory? Okay, so you have a solid and you're adding it to a liquid. So this is like if you've got your little petri dish and you drop a little piece of potassium, think about it like a little piece of salt. When you put that into the water, it produces hydrogen gas. So there'd be a gas that was coming out of the bowl, and you'd be left with this potassium hydroxide solution. So that would be something in the bowl that's molecule dissolved in water. That's what aqueous means. It means it's a molecule, it's a substance that's dissolved in water. So this may be colored, it may not be, but you'd have a bowl of this hydroxide and you'd have a gas coming out of it, is what you would observe in the laboratory. Okay, this one right here. So we can kind of look at these again. The first thing you want to look at is like what's happening here. So you've got copper, you've got this molecule right here, then you've got sodium, and then you've got this molecule right here, the PO4, and those are reacting to give you the copper and the PO4, and it's giving you the sodium and this nitric oxide molecule here. So this is giving you, again, you see this copper here is here, but it's with this guy paired up with it, and then the sodium right here is with this guy paired up with it. So that's going to tell you this is a double replacement reaction. This one's going here, and this one's going here. They're trading places. So we'll just write double rep here. Okay, let's see if we can balance this bad boy. So let's see. We've got a couple different things here, but we're going to write these as just like, I'll show you how we're going to write these. Copper is one of them. NO3 is going to be one of them. And the reason we're going to write these as the actual molecule is because you can see how they wrote these. They wrote these right here in parentheses. So we're not going to have these random oxygens moving around or these random nitrogens moving around. That molecule is going to stay consistent on both sides. So we're not going to worry about it too much. So this is the NO3. Then we have Na3. And then we have PO4. Okay, so on the left side right now, we've got one copper. Okay. We have two NO3s because NO3, 2. So we got 2 of these guys. We've got one Na3, and we've got one PO4. On the right side, we've got 3 coppers here. NO3, we've got one of those guys. We've got, excuse me, this shouldn't be Na3, this should just be Na. So we have 3 of these. Got ahead of myself. Okay, sorry. 3 sodiums, and we have 1 sodium on the right side. And then the PO4, we have 2 of on this side. So this one looks a little bit different than the other ones. We've got kind of all over the place, zigzagging. So let's start with 1. So let's start with copper. So if we make this guy a little 3 right here, because we want to match the 3 to the 3. So how does that affect everything else? We'll do it one more time here. So that gives us 3 coppers and 3 coppers. Sweet. Now it gives us 6 NO3s because we have NO3 squared times 3. So we have 6 of these guys now. And we've only got one of them on this side. Now on this, these don't change. So we have 3 NAs, and we have 1 NA. And then we have 1 PO4, and we have 2 PO4s. Okay, so now let's look at the next one we want to fix. Let's fix the NO3s. So if we've got 6 NO3s on this side, we're going to need 6 on this side. So let's put a little 6 there. Okay, now what does that do to all of our stuff? So we've got 3 and 3 for copper. Doesn't change. Okay. In fact, none of these numbers on the right are going to change. So this is, or sorry, on the left are going to change. So 6, 3, 1. We only changed a number on the right this time, so that's the only thing that's going to change. NO3, now we have 6 of those here. Cool, another little checkbox for us. But now we have 6 NAs here. And then we still have only 2 PO4s. Okay, cool. So now NAs. So if this side's got 6, we just added that. We need 6 over here. So since this is Na3, we do 6 divided by 3. Okay, what does that equal? Okay, we need 2. So we need a 2 here, because 2 times 3 equals 6. So a 2 here will give us 6 here. So we'll write that one more time. So we got 3 and 3. We didn't change our coppers. Now NO3, we have 6 of those. 3 times 2. Still have 6 NO3s here. Kind of draw a little parentheses around these to keep it straight. And we'll draw parentheses right here too. Make it easy on us. Okay, so 6 and 6, cool. 2 times 3, we have 6 Na here. We have 6 Na here. And our PO4, we have 2 PO4s now here. And this is 2 PO4s. All those numbers matched. That means we did it right. So it's a 3 here, a 2 here. This stays 1, and a 6 here. So we do the quick check again. Does any number divide into 3, 2, and 6? No. 2 doesn't go into 3, so that leaves us where that means this is our most simplified answer here. It's a double replacement. So the last part of this was, what would you observe as the reaction or perform in the lab? So you're adding an aqueous solution. So think of that again as something it's very similar to a liquid, but it's got stuff in it, with another aqueous solution. So you pour two of your test tubes together, and you end up with a solid and an aqueous solution. So what you would see as you poured those together was a solid would form in the dish, and there would be a different solution at the bottom of the dish. So you're actually using this to turn two aqueous things, two somewhat liquid things, into a solid and an aqueous solution. So hopefully that makes sense.